Welcome back to the Algebra 2 series, and today we're looking at a couple of examples in the hyperbola section. And graphing hyperbolas can be a tedious endeavor, but today we're going to try to make that as painless as possible, actually somewhat enjoyable if you like to do this. I certainly do. So we're going to try with this first one, and keep in mind from the last video a couple of things. First of all, since the x is coming first in the equation, that means it is a horizontal hyperbola. One of the things I remember about horizontal hyperbolas is that they kind of look like an H after all. They kind of open to the right and to the left, and so they have a familiar look to that if you're thinking H as horizontal. A couple of things to note here: the x is not paired up with any number inside the quantity, so that h must be 0, and the k is -1. Also, here we have 9 equaling the a squared, and 27 is the b squared. So very quickly, I'm going to put c squared is equal to a squared plus b squared, or in this case, I can just add a squared and b squared together to make 36. I'm adding them right here, and then that's equal to c squared. So c is going to be plus or minus 6, and then, of course, a is plus minus 3. Excuse me, let me rewrite that. So a is uh, plus or minus 3, and b is plus or minus root 27, or 3 radical 3. Radical 27 is easier to visualize on the coordinate plane. Well, the nice part about this example is that we could graph it starting with our special little box. We'll start, of course, at the center, which is located at 0, -1. We'll just put a dot right there. And we're going to work our way around, starting with the actual box. Moving left and right 3 units, that is going to give us our a values. So I'll try to do this in somewhat of a neat fashion. That didn't look very good. Let's see here. I want to make these units look at least somewhat decent. Close enough. That's going to be our a, and that's the a going the opposite way. The b is going up quite a ways. So radical 27 is a little more than 5, so I'll put it up there a little more than 5. And a little farther down. Okay, now keep in mind that we're making a box out of this thing. So we go straight up, we go straight across, and that way, when we create this box rectangle, we can see that, drawing the perfect rectangle there, that we can now draw in the diagonals, which create the asymptotes for the graph. And draw this way. It looks like we're going to run right into our equation up there, but that's okay. Keep in mind, of course, that this is horizontal. So being horizontal, having the x first, that means I need to create an h, and that tells, oh, excuse me, that's not right. Um, that's not right. Here, down here is my vertex. There it is. And here's the other one. I went up too high there. There's my center. Here's my vertex and my other vertex. And so if I carefully graph this, I'm just going to go straight up along the box and then out along the asymptote. And I move along that asymptote kind of like a dog runs along a fence, rather than, what I don't want to do is I don't want to do this, because that would create almost a parabola look to it, and we would be disregarding our asymptotes. So the asymptotes being guides for the graphs, and that's how we've got it. I would have to say that right-hand side is quite possibly the ugliest looking hyperbola I've ever seen. But anyway, that's okay. We do see as well that this hypotenuse, if you recall, the um, the hypotenuse of the AB, let me take a look at this more closely. Here's A, and here's B, and C is supposed to be that length. That's what C is. So we could generate our focus by finding that. And of course, you know that's 6 already, so that should check out. But that's the length that we're looking for. So let me go out 6 units. So that's 3 more. 1, 2, 3, because I already came out 3. So that would be where my focus is located. And here's my other focus. So we have a center, we have vertices, we have the foci, and then we have our box points, and that's there. I just call those BP. That's not British Petroleum. That's box points. And so that's where we come up with the values there. So that's the picture. And the last thing I need to do on this one is make an organized description of everything that's on there. So if it's all right, I'm going to erase this part of it, and I'm going to create for myself a little box over here. Rather than labeling things on the graph, I like to do it in a box, starting with the center, and then I'll do the foci, the vertices, then the foci, then the box points, and lastly, I'm going to leave a space at the bottom there to put in both asymptotes. So the center, of course, 0, -1. The vertices are going to be plus or minus 3, -1. The foci, plus or minus 6, -1. And the box points are going to be 0, -1, plus or minus, I'm running out of space here, 2√3. There we go. Uh, that because, oh, I'm making all kinds of mistakes here. Let's see here. That should be 3 radical 3. I suppose you were just giggling to yourself while you were watching this, saying, Mr. Rubash, what are you doing? Okay, so there you go, box points. The last thing we need to do is put in the equation of the asymptotes. And if you recall from the last video, we're going to write it as y minus k is equal to the slope x minus h. And the slope is going to be able to use a plus or minus. This one has a positive slope. This one has a negative slope. And we can just put a plus minus in front of that. In this case, the vertical length or the rise is b and the run is a. So this is going to be plus or minus b over a in this case. That's a little different from the video because in the video I did this for a vertical hyperbola. That's from the last video. So let's go ahead and finish this out. That would be y minus k, which of course is in this case y plus 1, equals plus or minus. Now the b turns out to be 3 radical 3, and the a turns out to be 3. So that would just make radical 3 the slope of both asymptotes, plus or minus. And that's just going to be x because there's a 0 for that one. So y plus 1 equals plus or minus radical 3x. You don't need the parentheses around the x. Well, that's supposed to be a simple one. Let's move on to one that's a little bit trickier. This one isn't so tricky, it's just that it's in a form that's somewhat undesirable. We're going to have to complete the square for x and y in order to get it into the proper form. So what we'll do is we'll actually work this out. First of all, let's get all of our values together, the 4y squared, and then minus 4y. I'm going to take this 4y to the other side. So we're cranking out some algebra now. Minus 16x squared. Move this over there, minus 32x. And then that's going to equal 19. Now this is one of the trickiest completing the square problems that we have in Algebra 2 because of the fact that we have this negative right here. Let me show you how this works out. First of all, we're going to factor the 4 out so that we have a coefficient of 1 on our y squared. That's minus y. We'll leave a blank here. Then in the second part, we're going to take out 16, but we're also going to take a negative out of that. So 16 is coming out, and look what shows up on the inside. It's x squared plus 2x. That was tricky. And that equals 19, and I will leave 2 blanks over here to help us out with that completing of the square. Moving down to the next step, this is y something squared minus 16, and this is x something squared. All right, so I'm about to complete the square. Taking half of the middle term gives me minus a half. Square it, you get plus 1/4. Multiply it by the 4 that precedes it, and you will get plus 1, and that's what we're going to add to the other side. That was very tricky. In the second completing the square, we get half of 2, which is 1. 1 squared is 1. 1 times 16 is 16, but recall, folks, that this is a minus over here. And so minus 16 means we need to subtract 16 from both sides. So once again, I find that this is one of the trickiest examples because if you add 16, you would get 36, which is actually kind of a nice number to get. Instead, we end up with 4. Okay, so that is the beginnings of our standard form. Finally, we'd like to generate a 1 on that right-hand side. So I'm going to divide everything by 4, And if I do that, I get y minus a half squared minus 4 times x plus 1 squared equals 1. And I've got my uh, problem set up in standard form. I don't like the look of this 4 right here, but I remember this. 4 is equal to 1 over 1/4. A little math trick from 5th grade math way back in, I won't say when. But anyway, y minus a half squared minus x plus 1 squared, and this is going to be over 1/4 equals 1. And just for fun here, I'm going to put the y minus a half squared over 1. What we've managed to do here is put it in standard form, and that's going to help us because now we can graph it. I'm going to slide over our Cartesian plane, and now with all the information that we have, we ought to be able to graph this guy. Of course, I'm going to start to build my box over here. One of the things that I'm going to find is that this is actually quite a difficult problem for many reasons. It has a lot of little traps in it, um, not to mention just the mechanics of getting to this point were difficult. So, of course, the center, this is tricky already. The x comes second, so we have to be careful there. That's negative 1, comma 1/2. That's tricky. One thing we do see here is that a is equal to the square root of 1 or 1. But this one is even tricky because that's b squared, so b is equal to a half. That's one of the strangest parts about that denominator is that if that's b squared, then b is actually a larger number than the b squared. So b equals a half. So a squared plus b squared equals c squared. And I'm going to work on that focus computation in a little while. For now, let's just go ahead and graph it. That would be the best thing, just to kind of give us a little feel good here. This is going to be at negative 1, comma 1/2, which is right about here. And we have to go up and down 1 unit for the a value. So if we work our way up and down 1, that would put this point here, and another point down there. Those are our vertices. Just put a little tiny v in there. To the right and left, we have to go half unit. Now, I see already that this graph is just way too small. I can't see that at all without putting my glasses on. So let me make this a little larger. That's better. There we go. Nothing wrong with redoing things once in a while. Here we go. And we're going to go up 1. Come down 1. That's much better. Left and right a half. And then from there, I'm going to create my box. There it is. If you hear something in the background, that's just the sounds of progress. There we go. And there we go. Making my diagonals because these are the asymptotes that will help us graph. Once again, if you label these parts, this first part here is the center, then we have the vertices on the top and bottom. This is a vertical hyperbola, so that puts this as a box point, and this is a box point. This graph is taking a long time to produce, but boy, it is rewarding when we get it done. This one goes along that asymptote and then down along that one. It also goes up along these two asymptotes. So we've got everything taken care of except our foci, but you know, I can always slap in the foci like this, and then we're just estimating anyway. We know what that computation is going to be, and we'll put that into our final box in just a minute. All right, let's get our points taken care of. The vertices go up and down from the center. So negative 1, comma 1/2 plus or minus 1. That would be the first part, going up and down 1 unit. The foci are negative 1, 1/2, up and down. We don't know yet. So that one we've got to compute right over here. Let's just do it up in the corner here. A squared is 1. B squared is 1/4. That's c squared. So c squared equals 5/4. C is plus or minus root 5 all over 2 if I take the square root of 4. So I'll plug that in right here. Radical 5 over 2. That's a bit messy, but that's all right. And then the b value is going to be negative 1 plus or minus, I'm going left and right, 1/2 unit, that's the b value, and up 1/2. As you can see, those are not very desirable values. However, the nice part about this one is that the slope, rise over run, the rise is a, the run is b, and so 1 over the b value of 1/2 equals 2. So we see that is our m in the equation of our asymptotes. So the asymptotes are not that hard. In this case, it's going to be y minus 1/2 equals plus or minus 2 times x plus 1, using the center point as our point in the point slope form. Well, I hope that you somewhat enjoyed the process of graphing these hyperbolas. Hopefully you will have some success as well. Obviously, completing the square carefully is important, and then organizing your work from there on out. We will have a couple more videos to kind of, summarize some more of these and maybe do some trickier problems, but hopefully this gives you a good idea on where to start.